All right, so these are temperature notes. So we're going to go over these notes in terms of temperature. Some of the stuff we've already talked about, so I'm not going to talk a lot about it, but we'll move on from there. So we're going to talk about temperature and how is temperature measured? Well, we already talked about temperature being measured by Celsius, Fahrenheit, but the unit that we're going to use for this unit is Kelvin. And Kelvin is an SI unit that measures the temperature with 0 being absolute 0. Okay, and what does the temperature mean? Well, temperature, like we know, is the average motion of particles. So Kelvin really measures the average motion of these particles. The symbol that we use for Kelvin is capital K. Okay, and the conversion to go from Kelvin to degrees Celsius is you take whatever degrees Celsius you have and you add 273 degrees, and that's how you get Kelvin. If you want to go from Kelvin to Celsius, all you have to do is subtract 273. So up here, if we want to convert the following temperatures to Kelvin, well, all we have to do is add 273 Kelvin to the degrees Celsius, and what do we get? We get 298 degrees Kelvin. Pretty simple. Same thing for this one. We start with 100 degrees Celsius. We add 273. What do we get? 373 Kelvin. Pretty easy. Now, if we're going the opposite direction, like we said, if we're going from Kelvin to Celsius, we have to do the opposite. So instead of adding 273, we have to subtract 273. So if we start with 273 degrees Kelvin, we subtract 273, what degrees Celsius do we have? We have 0 degrees Celsius. What about this one? We have 373 degrees Kelvin. We subtract 273. What do we get? We get 100 degrees Celsius. All right. So why exactly do we use Kelvin? Well, the reason we use Kelvin, and we talked about this already, is that Celsius to Fahrenheit scales can be negative. So they can represent temperature as a negative value. Well, we don't want to do that because when we're measuring temperature, we're measuring the average speed. And a negative number does not accurately describe particle motion. All right, so the lowest point on the Kelvin scale is 0, which is called what? Called absolute 0. All right, and absolute 0 is the point where all motion stops. So that's 0 K. Well, exactly how cold is that in Celsius? Well, 0 degrees Kelvin is negative 273 degrees Celsius. What about Fahrenheit, which is what you're used to? Well, in Fahrenheit, it's negative 460 degrees Fahrenheit. It's pretty cold. Okay, so now we're going to talk about the combined gas law. So you guys might remember from the notes that you did, these notes, right? So it's the first set of gas notes that we did, these equations here. So what do we notice about these first three? Well, they all have pressure in them, right? And then this bottom one has volume and temperature. We can actually put all three of these, or all four of these equations together. Okay, so if we look at the relationship between pressure and temperature, and then the relationship between volume and temperature, and then the relationship between pressure and volume, well, we can combine all three of these to look like something like P1, V1 over T1 equals P2, V2 over T2. Yes, we have this number thing down here, and if we were to add the number thing, just like any of the other ones, the number would go on the bottom. But you guys actually aren't going to be dealing with any equations that are dealing with numbers, so I'm not even going to add it into the equation. All right, so this right here is something called, if we go back to the notes that we're on, the combined gas law. P1 V1 over T1 equals P2 V2 over T2. So basically what this means is that the proportion of your pressure, your volume, and your temperature of an initial situation is going to be equal to the ratio between your final pressure, final volume, and temperature, okay? So we know that pressure and volume is inverse. We know that pressure and temperature is direct, and so is volume and temperature, both direct. So we can use this equation to help us solve problems. So let's take a look at this example problem that's right over here. So it says a tank of oxygen gas with a fixed volume. Okay, so it is a fixed volume of 20 liters. So that we know is a volume. Then it says it has an initial pressure of 1 atm. Well, initial pressure is P1. What are you starting with? You're starting with your initial pressure. So this is P1. Then it says, and a temperature of 300 K. Well, this, since this is what we're starting with, ends up being our T1, our initial temperature. So then the question says, what would the final pressure be? Well, what do you think final pressure is? Probably P2. What would the final pressure be if the temperature was dropped to 200 Kelvin? Okay, so this over here is T1. What do you think this is? This is T2, your final temperature. Okay, so since we're using this combined gas law, well, if this container has a fixed volume, that means that V1 and V2 are both going to be 20 because it cannot change its size. So if we were to plug this into our equation over here, well, what's P1? P1 is a 1. What is V1? V1 over here, we said is 20. What is T1? T1 right here is 300. That is going to be equal to P2 V2 over T2. So what is P2? P2 is what we're trying to find. So P2, we don't know. V2, right, we already know is still 20. Okay, then what about T2? T2 is 200. Okay, so in order to solve this, what you have to do is you have to cross multiply. Okay, so just like when we were doing density, we're cross multiplying. So 1 times 20 times 200, and then you're going to do 300 times P2 times 20.